So the last lecture was all about learning what energy auditing is all about. We talked a little bit about some of the codes and standards that are used in this industry. And I realized that opening the class with that content, it's a little dry, and I totally get that. But I think it is important to establish some of those key concepts and ideas that we're going to see over and over as we go through the semester. Today, we're going to continue on that road, but I think today is a little more interesting because we're actually going to be talking about mechanical equipment and how we look at equipment and how we define what efficiency means. So first up, let's talk about the basis of energy use. So anytime we are talking about energy being used by a system, it comes from this equation right here. So the energy use is going to be based on the energy use rate, which is going to be your power. So most commonly, that's going to be kilowatts if we're talking about electric power, or if we're talking about gas use, that would be in BTUs per hour. And then our operating hours, so that's going to be our time component. So we have an instantaneous component to this equation. That's going to be our power. And then we have the time component, where if we have some power over a certain amount of time, that's going to result in some kind of energy use. So if we're looking at an energy using system and we're thinking about this equation, if either of these terms, power or time, is small, then there's going to be less opportunity there for energy savings. So the reason being, if that system that you are looking at isn't using a lot of energy to begin with, then there's not going to be a lot of opportunity there to save energy if they're not using it to start. And a common refrain around our office is the most efficient system is the one that is off. It's not using any energy. So to help illustrate this idea, if you went to a customer and you said, you can save 60% of the energy of this system. Well, 60% of what? 60% of a small value is still a small value. Conversely, if both of those terms in this generalized equation, if they're large, lots of power, and it's running for a lot of time during the year, then you're going to have a big opportunity there. So some simple examples. A bad opportunity. Let's say you have a large 75 horsepower fan. So that would be a big power component, but it's only running a handful of hours per year. Or if you flip that around, you have a small ceiling fan that runs 7,000 hours per year, which is a large majority of the year, but it only draws 50 watts of power. But a good opportunity would be a large pump, say 100 horsepower, and it's running a lot of hours in the year, say 5,600. So you would look at that pump and say, that looks like a prime candidate for some energy savings. And this leads into the basis of savings concept. So I'm going to be throwing a lot of terms at you today. The first one is what we call an ECM, which is an energy conservation measure, which I'd say is a generic term. There are many, many terms and abbreviations that are expressing the same idea, but I think the most common one is ECM. And what an ECM is essentially a proposed solution to save some energy. So this is a recommendation that you would make to a client. And if you're going to present those savings to a client, you have to be prepared to answer the question, what is the basis of savings? So if something is going to save energy, there should be a clear and understandable basis of savings. Or restated another way, how is energy being saved? And usually we look at this from two perspectives. So we have what we call the baseline condition, which is essentially this is how we found it before we've done anything. And then we have what is the proposed condition? What are we recommending they do? So this baseline and proposed conditions are kind of like a before and after. And so if you are recommending an ECM to a client, you're making a recommendation on how they can save energy, you should be able to answer these questions. What is the basis of savings and how is energy being saved? What is the baseline condition and what is the proposed condition? An easy example, let's say you upgrade your air conditioner. So your basis of savings in this case would be you are improving the cooling system efficiency. So this new air conditioner is going to be more efficient when we're done compared to how efficient it was as you found it. So how is efficiency measured? So first up, we need to talk about the importance of energy input versus energy output. And this is an extremely important concept in this course. What's going in versus what's coming out. And so if somebody gives you units of power or energy, you have to know, are they talking about input or are they talking about output? And the general term that differentiates these two terms is efficiency. Thankfully, it's a very simple equation. So efficiency is going to be your output over your input. Your output is always going to be less than your input. I mean, you can never put more in than you get out at the other side. Or we can rearrange this and say the input is going to be our output over our efficiency. And the reason that's important, which I'll have an example that talks a bit more about this, is the input is what you actually pay for from your utility company. So we'll come back to that. Efficiency is generally expressed in percent, 0 to 100%. But this is just one term. And as you're going to see today, there are tons of efficiency metrics in HVAC. Your eyes are going to glaze over probably here in a bit. And which metric we're going to use typically depends on what kind of equipment we have, how big it is, what kind of fuel are we using. Is it an electric source? Is it a gas source? That will impact how we express efficiency. And then it's also important to think about series efficiency. So if you have multiple processes in a line, the efficiency of that entire series is going to be the product of all of the individual efficiencies in that series process. I'll have a diagram here to talk more about that. So to put this idea of efficiency into a simple diagram, so let's say you have a simple process. You're going to put some energy in, you're going to get some energy out, but because processes aren't perfect, you're going to have some waste, which means that ultimately you are going to have to put in more on the input side than you get out on the output side. So to put some actual numbers to this, if we have a 60% efficient process, let's say we put in 100 BTUs, which is what we're going to pay for from the utility company. We're going to get 60 BTUs output, which is the actual useful thing at the end of our process. And then 40 BTUs will just go off as waste due to the inefficiency. And this idea of what's useful, this is something that I've always found very helpful to think about in terms of input and output. So this output is what is the useful thing that we get out of this process. In HVAC, that's probably going to be something like heat output. If you're trying to heat your building up, the heat output of a process, well, that's the useful part. Or if you're running a motor, you're trying to get some output on that motor shaft, and that's going to have a process as well. On the other side, this input, think of this as what the utility needs to deliver for you to get that useful output out of your process. So the utility company is providing you electricity or natural gas. And in this scenario, they have to give you 100 BTUs. Even though you only want 60 BTUs output, you still have to pay for 100 BTUs on the input side of this process. And to help illustrate this series efficiency idea, so in this case, we have 3 processes that are all in a row. So you're going to feed something to the first process, which then goes to the second process and to the third process to get something out the other side. So let's say this first process is 90% efficient, the second process is 85%, and the third is 88. Individually, all of these processes are pretty efficient. I mean, anything above 80%, that's pretty good. But the problem is, because of that series efficiency equation, where we're going to multiply this all together, you're going to see that the series efficiency of this entire staged process is only 67.3%. Well, that's not very good. So you can see that even if you have pretty efficient individual processes, when you start putting them together, you can end up with a fairly inefficient overall process. And this series efficiency uh, concept is going to come back several times throughout this semester. So let's talk HVAC. And how do we measure HVAC efficiency? When we're talking about this kind of equipment, efficiency is not a constant. There's going to be all kinds of external factors that are going to impact how efficient our equipment's going to be. The most apparent example that we see is a standard air conditioner that's going to cool down your room or your building is going to use more or less energy depending on the outside air temperature. As an example, and we'll talk more about EER here in a minute, just know now that a higher EER value means we're more efficient. If we say air conditioner 1 has an efficiency of 11.5 EER when it's 90 degrees outside, reasonably hot day, so we'll probably need to run our air conditioner. And the second air conditioner has an efficiency of 12.6 EER when it's 85 degrees outside. And so if somebody were to present you with this information and said, which one of these is more efficient? And we really can't say, because that efficiency value is going to vary with that outside air temperature. So because one of these is expressed at 90 degrees, the other is expressed at 85 degrees outside air temperature, we don't know which one is more efficient. So generally, what they do is these metrics are going to be expressed based on specific conditions, so that you know when you look at 2 units, which one is going to be more efficient. And it's typically certified at those standardized conditions. So in that previous example, same units, but let's say we've now tested them at the same conditions. Air conditioner 1, same efficiency, 11.5 EER when it's 90 degrees outside. But that second unit, now we've expressed the efficiency at a higher outside air temperature, and now the efficiency has dropped. And so now you can see, well, air conditioner 1, that is the more efficient option in this case. The reason they do this is this allows different manufacturers to compare products side by side. So if you're looking at air conditioners from 2 different manufacturers, this ensures that you can actually compare them apples to apples, and you don't have one side trying to game the system by optimizing these test conditions to get a higher efficiency rating. And so as an example, here is a air conditioner that we used on one of our projects, and the important info here is that 11.1 EER. And you can see just above that, this is tested at AHRI 360 standard conditions, which if you were to look up that standard, you would see the standardized test conditions for where they derived that 11.1 value. And if you looked at a different manufacturer, they would say the exact same thing. Their efficiency would be rated at that same AHRI 360 test condition. You need to be a little wary of salespeople and efficiency claims for this reason. And I'll have a more concrete example here in a minute. Well, what if somebody was trying to sell you some equipment and they said this unit is up to 99% efficient? Well, okay, up to 99%, but when is it 99% efficient? Could it be 80% efficient at some different conditions? The other thing to keep in mind is the efficiency metrics are often expressed by 2 different values, either the full load values, which means that unit's running maxed out, and then a average seasonal values. So over the course of a typical summer, what's going to be the average air conditioning efficiency? So we'll come back to that. So here is an example of a condensing boiler, which we'll talk about more in depth when we get into hot water systems down the road. But if you look at this condensing boiler cut sheet, they give you all these features and they tell you how great this thing is. And if you notice, they say efficiency up to 99%. And that's a pretty important language choice there, to say up to 99%. And it's back to that argument of, well, under what conditions is it going to be 99% efficient? So not all equipment has these strict standardized testing measures enforced, and this would be one example of that. With fuel-fired equipment. So this is what I like to start with because fuel-fired equipment is pretty easy. So anything that uses fuel to heat something through some combustion process is going to use efficiency as its metric, which we already talked about. Efficiency is a very easy and simple number to understand. In HVAC, the most common example is your standard household furnace. So any of you that live in a house, unless you have electric baseboard heat, you probably have a central gas furnace that's then ducted through your house. And the basic idea here, you burn gas, you heat up some air, blow it through the house. Most common fuel is natural gas, which is mostly methane. Some of the less common options would be fuel oil, propane, or kerosene. The big difference there is those other fuels typically are not provided by a utility company like Avista. If you have natural gas in Spokane, 99% chance that it is provided by Avista. And they have gas lines running through the entire city. If you have a fuel oil furnace, you have to go buy your fuel oil from Joe's fuel oil shop down the road. Most fuel fired equipment is around 75 to 80% efficient. And that is kind of the standard efficiency baseline you can expect with gas fired equipment. The code, energy code, today says that any new gas fired equipment needs to be at least 80% efficient. And what that means is the rest of that 20 to 25% of that energy from combusting that gas just goes out the flue. So to put this in a process diagram, again, we have a 80% efficient gas-fired process. We get 100 BTUs from the utility company. That's what Avista provides us, and that's what we have to pay for. We get 80 BTUs output. And so that actually is what is the useful output. So that 80 BTUs is actually what goes into the air, which is then blown into your house to keep it warm. And then you get 20 BTUs of waste that just gets dumped outside. To make it a little more visual, here's a schematic of what that looks like. So in your house, you're going to pull that cold or neutral air from the house from throughout many rooms in your house. That's going to get pulled into the furnace where there's a gas-fired heat exchanger. That's going to combust gas, heat up the air. You get about 80% of that energy. The other 20% goes out the flue. And then that's going to blow warm air into your room, where then it gets sucked back in on the cold side, and it's just a ongoing cyclical process. And there's your waste combustion gas. It's kind of hard to see in this diagram, but that's what this white pipe is going to. So this would need to get piped to the outside of the house, because you certainly don't want to be dumping that inside your house. And that's really it for gas-fired equipment. So gas-fired equipment is pretty straightforward and simple. When we get into cooling systems, that's where it gets a lot more complicated. So for cooling systems, it generally comes back to this energy efficiency ratio, also known as EER, is the abbreviation. And that is going to be the basis of cooling system efficiency. And how this is defined, the EER is defined as the BTUs per hour that you are removing divided by the watts input that you need to put into this machine to make it do its job. So translation, how much heat can I pull out of a room per watt of electrical input energy? Generally, higher is better. If I can pour more, if I can pull more heat for the same wattage, that would be a higher efficiency, a higher EER. Or if I can pull the same heat for less wattage, that would be a higher EER as well. And note that BTU per hour is an instantaneous term. So that would be analogous to power, because that's BTUs per hour. And as a reminder, I'm not sure how much, if at all, HVAC was covered in any of your thermodynamics classes. I know when I was going to school there, if at all, they only briefly touched on it. But I remember really not knowing anything about HVAC going into this industry. But as a reminder, air conditioners don't make cold. That would be breaking the laws of thermodynamics. You can't just make cold. That's not how an air conditioner works. An air conditioner moves heat energy from inside the building and then dumps it outside. So it's just moving heat. And that EER value is based on the heat removed from the space or the room or your house or your building, not the total heat that we're dumping outside. And this statement will make more sense here in a moment. So back to these process diagrams. If you have a room you're trying to keep at 75 degrees, which is a fairly common temperature to maintain, and you have this air conditioner whose job it is to keep that room nice and cool. Well, let's say that air conditioner is removing 3,000 watts of heat. And back to this idea of this is the useful part. This is the part of the air conditioner that is its job. How much heat can I take out of the space? To run that air conditioner, we need to put in 1,000 watts of electrical input. And so that's what's coming from the utility company, and that's what we need to pay for. And then if you have two arrows going into this process, it's going to sum up to a total of 4,000 watts of heat dumped outside. So recall in last lecture, a big concept to remember is every watt of input energy will become heat. So if you're putting in 1,000 watts of electricity, that will turn into heat in addition to this 3,000 watts that we're pulling from the space. And so you're actually dumping 4,000 watts in total outside. But if you think back to how EER is defined, it's BTU per hour removed from the space, because that's the useful part and that's the thing we care about. We don't necessarily care about this 4,000. So if we do the 3,000 watts, and then we need to convert that to BTUs per hour with that 3.412 conversion factor, divide by our watts input, and we end up with an EER of about 10.2. So that's the basis of EER. But one thing that is important to understand about that value is that EER value that's tested and certified at one condition. So if they need to get that certified by the AHRI standards team, they will take that unit and put it in a testing chamber. They will test it at one condition, and that is what the EER will be. And that's typically close to full load, which would be close to a maxed out operation with the air conditioner working as hard as it can. But if you remember, earlier I said, well, EER actually varies based on that outside air temperature. So in actual practice, your EER could be higher than that or lower than that, depending on how warm or cold a day you actually have. Because if it's warmer out, it's harder to move that heat. These air conditioners are using refrigerant to essentially counteract what the building wants to do. So if it's really hot outside, that heat is trying to heat up the building, and we are using the air conditioner to instead move that heat from inside to outside. Well, if it's really, really hot outside, if you go down to Arizona where it's 120 degrees outside, it's pretty dang hard to move that heat because it's already so hot. You're essentially pushing a boulder uphill. And conversely, if it's colder out, well, now it's easier to move the heat outside. So if you have a nice 80-degree day, you would still need air conditioning on an 80-degree day, but your unit is going to be more efficient because it's not as hot outside. It's going to have an easier time moving that heat. So the bottom line, this same air conditioner will have a variable EER depending on what is going on at that exact moment. And so this is how we arrive at this idea of seasonal average efficiency. One of the most common ones is the IEER, which is the integrated energy efficiency ratio. And the big difference here with the regular EER is this gets tested at multiple conditions with various loads. The IEER should always be higher than the EER. And I'll have an equation here that'll help illustrate that. So as an example, you could have a cooling unit, air conditioner, that has a 10.0 EER at full load conditions, but it could have a 13.5 IEER seasonal average. And so the average seasonal efficiency is going to be better than the full load conditions. Looking back at that same selection we had before, the EER is 11.1, and then right next to it is the IEER. And the energy code will have minimum values that you have to meet for both of these. So you can't just meet one or the other. The code will tell you values for each of those that have to be exceeded, which is why they list these values front and center on these equipment cut sheets. And you can see the EER is 11.1, the IEER is significantly higher, 19.9, which is very good. And that would tell me, hey, this is a very efficient air conditioner. 11.1, that's okay. It meets code, but it's nothing to get excited about. But this 19.9 is very good. And so this would be a better representation if I'm trying to think about how much energy am I going to save by installing this unit. That IEER is going to be a better representation of that versus the standard EER. So the equation, which might make your head spin a little bit, I won't read it out, but the idea here is they are trying to average out the EER across multiple operating conditions. So this first term, this has them test the EER at a 100% load, and then they weight that with a 2% weight factor. And then they test the EER at 75% load, so a little bit lower load. And this is weighted at 61.7%. And then a third test at 50% and a fourth test at 25%. So they have to come up with a operating efficiency at 4 different conditions, and then they weight those efficiencies to come up with an average. So they're saying that they're only going to assume this unit's operating at 100% load 2% of the time each year. And that's not a lot, especially if we are talking about an air conditioner, which might only operate 3 months out of the year. So it's not even over the full year unless you live somewhere where they have cooling year round. And then 75% load for a significantly more amount of time each year, almost 62%. And then 50% load at about 24% and 25% load at 12.5%. And so this equation allows them to account for these part load EER values, since that's the majority of the operating time. So this equation is saying that we understand this unit 98% of the time won't be operating at full load conditions. It'll be operating at some part load condition where it's probably going to be more efficient. And this is just one term, IEER. There are a couple other terms, the SEER, seasonal energy efficiency ratio, and IPLV, integrated part load value. They are calculated similarly, but they are used for different types of cooling equipment. So to try and sum this up a little bit. So gas-fired heating equipment. So this would be furnaces, boilers, water heaters, and unit heaters. So you could have gas-fired unit heaters. This would be something you'd typically see in a shop that maybe they don't need cooling, or in a barn, or some type of space like that, or more of an industrial setting. You could have gas-fired boilers, which running through this white pipe here in this picture, this is all hot water, or it could be producing steam. Gas-fired furnace, which we've already talked about. So you can see out the top here, so that's where the warm air would be pushed out. And then on the left-hand side, this is pulling in the colder return air, and then it's just running through that cycle. Or you could have a domestic hot water heater to serve all of your sinks and showers and anywhere you might need hot water for public use. So to review, efficiency is the general metric, 0 to 100%. But similar to EER, efficiency is expressed at one condition only. There is one other efficiency metric used with gas-fired equipment, which is the annual fuel utilization ratio, or excuse me, annual fuel utilization efficiency, abbreviated AFU. But again, that is 0 to 100%, but that is calculated as a seasonal average value. So kind of like EER, but for gas. And then we get into refrigeration equipment. So air conditioners, water chillers. So here's an example of a air source water chiller up on the roof of a building. So running through these gray pipes. The job of this unit is to produce chilled water and then send it out to the building. And this big device here, this chiller, is going to take in warmer water, reject heat to the outside, and then send it back colder than it came in. Or you could have a simple window air conditioner. We would typically only see that in residential applications. You shouldn't be seeing that in a commercial building, although I've seen my fair share. And then more on the commercial side, you could have a packaged rooftop unit. So this has a built-in air conditioner. You can't see it in the picture, but there's actually ductwork running down vertically from the unit. So it's going to operate kind of like a furnace, where it's going to pull in air from the building, cool it down using a refrigeration process, and then send it back into the building. So we talked about EER, which is BTU per hour removed divided by the watts input, but this is expressed at just the one condition. We talked about IEER, same units, but at the seasonal average. Briefly touched on SEER, similar idea to IEER, but at the seasonal average value. And it just keeps going. And I guess I should have started this by saying you don't have to memorize all these, but I do think it's important to at least talk about them. Integrated part load value, which again, seasonal average, same units. And then we get kind of an oddball one, which is kilowatts per ton of cooling. So that's units of kW input divided by tons of output, which is expressed at just one testing condition. Quick aside, a ton of cooling doesn't have anything to do with weight. 1 ton of cooling is 12,000 BTUs per hour of energy removed. And what's odd about this metric is it's actually inverted from the others. So this one is input over output. as opposed to output over input, like all of the other ones. And so what that means is that that kW per ton metric, lower, is actually better. And then we get into refrigeration equipment in heating. So previously we were talking about refrigeration equipment in cooling systems, but we can actually use refrigeration equipment to provide heating as well. And that's with a device that is called a heat pump. And this is a term I hope you're aware of from your thermo class, but the coefficient of performance, COP. COP is dimensionless, output over input, but typically it's expressed just at one condition. And then heat pumps also have a seasonal average metric called the heating seasonal performance factor, HSPF. And for some reason, no idea why, they decided to change the units on that. So the HSPF has the same units as EER and all of those, most of those other cooling efficiencies, where they use BTU per hour over watts. Don't ask me who came up with that, but that's the way it is. I'm not sure why they didn't keep it dimensionless like they did for COP. So to show how a heat pump works in a generalized diagram, so let's say we are in the winter months. We're trying to keep our room at a nice 70 degrees, but it's pretty cold outside. The way a heat pump is going to work is it's going to pull heat from the outside. So let's say we're pulling 3,000 watts of heat energy from the outside. And even if it's really cold outside, say it's 5 degrees outside, really cold day, a heat pump can still pull heat energy from that air. There is still some heat content there from which to pull from. It's not exactly easy to do, but it can do it. And let's say to run that heat pump, we need to put in 1,000 watts of input, which again, that's what we pay for from our utility company. And then thinking of the conservation of energy, if you have 3,000 coming in, 1,000 coming in, you actually get 4,000 watts out of the heat pump. Because again, that 1,000 watts of input that you're putting in to run the heat pump, that all eventually turns into heat. And then again, think about what is useful. The job of the heat pump is to heat the space. So ultimately, that's going to be that 4,000 watts that's going to be added to the space. That's the part that's useful in this. So to calculate the COP, we have 4,000 watts of useful output divided by 1,000 watts of input. And so we get a 4.0 COP. More to come on heat pumps. We'll have, I want to say, 2 or 3 lectures devoted to a couple different styles of heat pumps. But for now, all you really need to know is if somebody uses the term heat pump, that just means we're using a refrigeration process to provide heating to a building or a room. And this is achieved through taking that heat energy from the outside, bringing it inside. And if you've never heard of a heat pump, this might seem a little odd, because when you hear the term refrigerant, you think of a refrigerator. You think of things that provide cooling, but we can use that same refrigerant to move heat in the other direction. And fundamentally, this is the exact same process as an air conditioning system. We're just running it backwards in reverse. And if you have a heat pump, it's going to use those same components to provide heating and cooling. So a heat pump inherently could provide cooling as well, depending on the season. So you could end up running your refrigeration equipment year round. All right, that was a lot. A lot to take in. I totally get it. So to try to sum it up a little bit, gas heating, very easy. Efficiency, AFU, 0 to 100%. Refrigeration, that's where it gets tricky. So, I mean, these are all the terms I've just covered. So what's that? Seven terms to express the efficiency of a refrigerant-based system, which seems kind of overkill. But don't shoot the messenger. I am not the one who made that decision to use all those terms. Ultimately, though, all of those refrigerant uh, efficiency terms, they're all expressing the same idea of output over input. The only oddball in that group is that kW per ton, where they've flipped it around. So most of those are expressing the same idea, but they use different units, whether they're dimensionless or they're BTUs per hour over watts. And which one you're going to use or see if you're looking at equipment, it depends on a number of things. So you can have different types of equipment, chillers, air conditioners, heat pumps. All of those use different metrics. Depends on your operating mode. If you have a heat pump, you're going to have a EER efficiency in cooling mode in addition to a COP efficiency in heating mode, depending on what the heat pump is doing. Different conditions, whether it's a full load condition or a seasonal average efficiency. The equipment size can make a difference. Larger equipment may be rated differently. So for example, larger cooling equipment, the typical seasonal average metric is IEER, but smaller equipment is rated on SEER. And we have industry norms. I can't tell you why heat pumps are rated in both COP and HSPF, which have different units for how they're defined. I don't know why that is. Air conditioners are rated in EER, IEER, SEER. So it's a lot. I get it. It's a lot to remember, but just kind of remember it's all about output over input, and generally higher value is better, except for kW per ton. So you don't need to memorize all of them, but you at least have to have an understanding of when you might use one or the other, or at least what the term generally means. Conversions. Note that there's no direct conversion from full load values. So like an EER, if you have an EER value for an air conditioner, there's no way to provide a direct conversion to a seasonal average value. You could have two air conditioners that have the same EER value, but very different seasonal average values. There is a way to estimate it, but it's not perfect. I've used it in a pinch, but generally speaking, there is no direct conversion. kW per ton, again, a little unique, but we still can convert kW per ton to EER and COP. The first time I taught this class, I ran through the derivations for how these are determined, and the reaction wasn't great. So I'm just giving you these. If you really want to look up the derivations, be my guest. But EER is equal to the COP times 3.412, which can be rearranged to the COP is EER over 3.412. And then we have some similar conversion factors for kW per ton to EER and kW per ton to COP. And so using these conversion factors, we can hop back and forth depending on what efficiency metric is given to us. So if we are given a value of kW per ton, but we really like the simplicity of working with COP, which I really do because it's a dimensionless value, it's very easy to work with, it's pretty easy to convert between these different metrics. Ultimately, this is all derived from these two conversion factors. 3.412 BTUs per hour is equal to 1 watt, and then 12,000 BTUs per hour is equal to 1 ton of cooling. The derivations here aren't difficult. If you want to look them up, be my guest. But fundamentally, that's what it comes down to, is those two other conversion factors. And then a quick note on efficiency versus efficacy. So these terms are very similar sounding, and they're often used interchangeably, but efficiency and efficacy are different things. Efficiency is always used for similar units of input and output. In my world, you put energy in, you get energy out, or power in, power out, either way. Efficacy is for different units of input and output. So if you put energy or power into something, you get something else out. Some common examples. If you're looking at cars, you're going to buy a new car. Well, how many miles per gallon does it get? So those are different units. You can't equate miles to gallons. There's no conversion factor there, but you can't express the efficacy of a car as miles per gallon. In lighting, which we'll get more into lighting down the road, the common one is lumens per watt. Lumens being a measure of the lighting output of a light bulb or a light fixture. So how much light are you getting out of it compared to how much electrical input are you putting in? So a higher lumens per watt would mean it's a more, now I'm going to say efficient, but I'm telling you now that's not the right term, but you get the idea. If we're talking about airflow, if you're going to be running a motor that's moving air through your building, like in your furnace, sometimes that's measured in CFM per watt, CFM being cubic feet per minute. So how much volume of air per minute can we move per watt of energy or power that we're putting in? Let's close this up with a few notes on homework. So I hope everybody found the homework assignments on Blackboard. The one thing that is a little unusual is my grading policy, which if you looked at the syllabus in depth, this would have been described there, but I know not everybody actually reads the syllabus. So if anybody has had Dr. Capobianchi, at least the way he did his grading back in my day, he would grade one problem on your assignment. And your entire grade on that assignment was based on that one problem. And his thought was, well, you'll make a good effort on all the problems because you don't know which one you're going to take, or which one he's going to grade, rather. I think that's a little ruthless, but I can see the merit in it, especially when I don't have a grader myself. So I do take his approach somewhat. Essentially, I will grade 2 or 3 problems in full on each assignment, and I'll skim the rest. I do still want you to do the rest of the assignment. So those 2 to 3 problems, that's going to be the majority of your points. I want to say it's usually around, if I remember right, 6 out of the 10 points will be based on those problems. And then I just skim through the rest of your assignment, make sure you made a good attempt at the rest of the problems, didn't skip anything. That's an easy way to get the additional 4 points, or however the math works out. The important thing here, though, is after I've graded everything, I do post the homework keys on Blackboard. So it's really important to take a look at those, make sure you understand the concepts, come back with questions. I think typically that'll probably be more of a concern as we approach the test time. And all of my homework assignments at the very end, if any of you have started the first homework yet, you'll notice the last question is a bonus question. So I've done this every year, and I solicit feedback at the end of each semester, and this has always been a big hit. So there will always be some bonus question at the end of an assignment, and then I do share the results with the class. It's always a good way to kick off each day. So have fun with it and reach out with any other questions. So that's all I got for you today. Any questions? All right. Well, I am happy to stick around until 6:05. Most of my lectures do get over a bit early. So if you want to hang out, work on the homework, I can be available. But if all of you want to step out, then that's fine too.